Alright, hey guys, hello fellow neuroimagers. Today we're going to walk through 03-lab. Just going to cover some of the common gotchas that I saw and just try to emphasize the best practices in order to complete this homework. So, with that said, I already clicked on the little screen to get my terminal open, and now I will cd into Iowa. Oh, actually, one thing that I forgot to do is to start my screen keylogger. So I'm just gonna do that real quick. Okay. Alright. Alright. You guys don't have that installed because it would just be annoying if you guys had to deal with that. So I'm going to cd and UI labs studicant. Alright. And now I'm just going to open my Jupyter notebook from here. See that? Okay. So I didn't do some of the in-class exercises, but we will get things worked out. Alright. So now I've already downloaded the image, and it was saved as sub-01 underscore tu1w.nii.gz. Alright. So that'll make it easy for me to specify the spec command here. So bet, I already sped out the options before, so its basic organization is input, output, and the options that we want. And the only options specified in the directions is that we want a mask. So let's find the option that corresponds to that. It looks like -m, generate a binary brain mask, since the mask is just ones and zeros. So I'll do bet sub01 underscore tu1 weighted.nii.gz. That's my input, and now I'll specify my output, because that's how this command is organized. For some other commands, the options might go here, or and the output might be the last thing, but you can't really predict how an argument's going or how a command is going to be organized until you actually look at the documentation. So that's why it's very important to always look at the documentation to be sure that you are organizing the inputs the way that the command expects. So now the output will be underscore t1 weighted brain.nii.gz, and we just want a mask. So -m for that mask, and hit Shift Enter here, and that will run bet for us, and we will check on that. So let's look at sub, see how good it was, the brain, and we'll even add in the mask. Cool. So we will check. Oh, oops. Forgetting the very important thing that this is a bash. There we go. Couple of mistakes there, but we're on our way. Okay, so yeah, this image we see a little bit of wraparound. I guess they had the field of view didn't encompass the entire face. So we'll take that out, and we will check out the brain here. So yeah, with this we can see a little bit of bias. We can tell because it's super bright down in these middle areas here, and it's a little bit darker up here. But let's take a look at that mask, and let's see if I can make that a little less opaque. There we go. It looks like it matched pretty well. I'd say this is a pretty successful scroll strip. Maybe only misses little parts of the gray matter, but all in all, this one looks like a good mask. So now we'll do the code to run fast, and for that, as I think many of you did, just copy and pasted the command that we used. Before, and then just change out the input-output arguments. So, going to try to copy this, Control C. Paste it here, Control V. Okay, so now let's walk through the options real quick, see if I remember them too. The dash T means the type of image that you're inputting in, 1 being a T1, 2 being a T2, and I think 3 being a proton density map, which we didn't cover, so just pretend that doesn't exist at this point. And then dash N stands for the number of tissue classifications, so we want to divide it, well, just number of classifications. We decided that for 3, since the tissue kind of naturally falls under gray matter, white matter, and CSF. Again, if we included a whole bunch of skull or dura or some other type of matter, or if there's some type of pathology, such as white matter lesions, you could test out, see if forward worked, see if it would pick out those things automatically. But again, that's a lot more of a riskier option. And then actually I'll just start changing the arguments now before I walk through all this stuff, since it'll take a little while. So the output base is going to be sub-01 underscore T1 weighted. And that's just how I'm going to specify that. And instead of my T1 brain, it is going to be sub-01 underscore T1 weighted underscore brain. That's our output from the bet command, and we don't want to overwrite the other log that we wrote, so this is going to be sub-01, I just call it fast.log. So again, I renamed everything because we don't want to overwrite any of the files that we generated, because if you're actually running an analysis, overwriting file names is a pain, and it makes it really hard to follow what you're doing. So I'll start running this. And then for G and B and capital B and V and O, I know that O stands for the base name that you want to name all the fast outputs. So that means all the outputs generated by fast are going to be prepended with sub-01 underscore T1 weighted. Let's take I'm gonna have to relook at the documentation here, so you guys will also see it. So G segments. So yeah, this is that binary image, i.e. a mask for each of the tissue types. And then there was the dash B, so that is the estimated bias field. So when I was talking about it being darker near the cortex and brighter near the center, there's kind of a bias field there that can be corrected. And then the capital B here is the output, the bias corrected image. So we should see a more even keel intensities after that command has been run, or after this fast command finishes. And so we might be waiting a little while here. And then V usually just stands for verbose. Another comparison that we can draw here is that even just opposite to bet, all the options that we're specifying go before the input files. So even within FSL, it's not consistent on what commands do what, since bet is an FSL command and fast is an FSL command. See, with bet, we specify the input and the output file names even before we specify the options. Whereas for fast, we specify all the options we want. Then we specify an output base name. So not the name with the extension .nai.gz, but just the base name so that the fast can know how to name each file, in which there will be many. And then finally we pass in the input. So it's almost the exact reverse order of bet, where it goes options, output, input. And this little symbol right here is just a redirect. So that means normally things are printed out to the terminal or to the output portion of this code block. This is telling this command to push or to put all the output from this fast command into this log right here, or to this file that's named sub-01 underscore fast.log. And this file does not need to exist beforehand. It will create it automatically. So while we're waiting on that, we can begin to construct our other commands in order to complete the assignment. So once that finishes, we will make code to estimate an affine transform. Name your image sub-01. Okay. So we have the starter code in the lab here. So I'll do shift click. Alright, so I'll do shift click, control C. And I'll do control V. Okay, so again, we're going to want to rename some of the inputs here. For flirt, in the lab, the appropriate input can either be sub-01 underscore T1 underscore T1 weighted underscore brain.nai.gz, or it could be the restore version. So that's going to be output by fast, and what that means, that's the bias corrected image. So we'll take a look at that when the image is done, but we'll just use the bias uncorrected image for flirt right now. Actually, I'm making sure, did I copy everything that I needed to copy over? I'll copy all that stuff. I guess that will copy as soon as the other stuff is done. So, in fact, I will just copy that inside the terminal. So cd into UI labs 03 lab. Okay. So now I'll do Control Shift V. Control Shift V. Now I'll copy everything. Okay. Now we got all the M&I bits. And I can check on the status of the log right here. So if I do cat7 underscore fast. Okay. Looks like it might be getting close to done. Oh, okay, yeah, it looks like it finished, so I didn't even need to do that copy paste. Alright, So with that in mind, we'll actually take a step back and look at some of the different outputs. I'll just insert one more cell below. I just want to look at what they are named. I'm pretty sure they are named what I would expect. Okay. So FSL view, sub, I'll move this up a little bit. FSL view sub dash 01 underscore T1 weighted underscore brain dot ni dot gz. Then I'll also look at, again, you can just either type it all the way out, or you can use the tab autocomplete after you type a few letters. So let's take a look at this difference here. So the top image is the restore. Again, let's take a look at this bias correction. So, alright. So we see this is the image with the bias still intact. So it's still biased, and there it is, the unbiased image. So we can see a little bit more homogeneity across the entire brain instead of having the lower values up top. So if we click between, we can also see that numerically. In the restore, up here we now see 180, whereas in the unrestored or the biased image, it's 167. So that just matches. Didn't mean to make that one blank. That just matches our conception of the reality that we saw. It's really just like kind of just all around the edges that we see that bias. Okay. And the functional consequence of that is if those values are, if the bias is too much, and the FLIRT algorithm is essentially just comparing intensities between the image that you want to be registered, which is going to be our subject T1 brain, and relative to our template. So this is the MNI brain that we're looking at here. So potentially, if there's a lot of bias and the values in the middle are super bright and the values on the edge are super dark, there could be some strange fitting occurring where it may not be optimal. But for most cases, that is not the case. So let's walk through this FLIRT command. So the input, we're just going to use the biased input because we like to live dangerously. And for the reference, we are going to use the MNI brain that we copied over to our directory. Then for the output, we are going to call this named for us. So this is going to be called sub -01 -T1 F. And then the output matrix is going to be sub -01 dash. Okay. Cost function, correlation ratio, degrees of freedom, 12. And then the search X, search RY, search should be the Z one here. But that is the default, so it will do that for us automatically. And all that's saying is we can't rotate the brain more than 90 degrees in any direction. Because say, if the left-right, if there is a flip in the brain that made it such that the FLIRT algorithm said that there is a minimal cost in this orientation where we actually have to flip the brain around, then we would lose context of which side of the brain is left and which side of the brain is right, and maybe even up and down, and it would probably just look really ugly. So this helps constrain the search of FLIRT so that we keep it within reasonable bounds and that we don't lose, say, any anatomical accuracy. Okay, so with that said, I have changed all the command names, so I will run this FLIRT command. And as we let that run, we will set up our FNIRT command. FNIRT. So again, do shift, click. Oi. Okay, don't right click. Just Control C. Now do Control V. So, yeah, I don't believe we need the two IOUts, but we'll just leave that in there for posterity's sake. And the input is going to be, instead of the brain, the nonlinear transform from FSL does better with the optimization of the transform if the skull information is also included. So the rationale for this is that the definitely skulls between they kind of have a basic shape that we would like to maintain. So everyone has eyes and a nose and a skull that's surrounding the brain. So it kind of provides a nice ground truth for the algorithm to not go too crazy manipulating the transforms. So for the input, we're just going to do sub-01 underscore t1 weighted.ni.gz. So now we need to change the affine, since that is going to be different now. So we need to do sub-01 that. Okay. And then we should add, since again we don't want to overwrite previous outputs, so I'm actually going to append sub-01 dash sub-01 dash. So all these out flags or options mean that this is going to be the name of a particular output. So again, from the class example, we don't want to overwrite all of those that we did, so we are just going to rename these so that we don't overwrite those. So this is a config, so it's not an output. This is something that's being read in. And similar with the affine transform, that's something that's being read in. So now then, with the reference, that's the file that we copied over. And this one's now containing skull information as well. As if you had a keen eye, you could notice that the reference here was the brain, and this one doesn't specify the brain, which usually by default means that we are also including the skull. And then ref mask here is more like the region that we most care about during the fitting. Alright. And then, oh, I might butcher this one, but if I recall correctly, the warp resolution is how much it downsamples the image. So right now we're at, say, 2 by 2 by 2 when we're trying to when we're looking at the resolution of our image. This is going to downsample that to 10 by 10 by 10. So this just makes it a little bit more practical, so it doesn't take forever to run this. In fact, I'm going to start running it now that we got everything renamed. Start running that now. And yeah, this is essentially the way that we can look at just to downsample the resulting image so it doesn't take forever to estimate the nonlinear transform. So this is essentially the space in which it's determining the warp fields. So, in fact, just so that we can provide a little bit of context on this config, let's see if I can find that for you guys. So that does actually exist. It's an actual file. It's just not within here. It is within the FSL place. Let's see. What if it'd be in data? Probably not. Nope. So let's go to 5.0. Maybe it's in etc. Let's go to episode conf. Well, you know what? I think I will just submit a find command, and that will look for this file name for me. So shift click, Control C, and then remember to copy and paste in the terminal. It is going to be Control Shift V. I'm just going to look for anything that vaguely looks like this file name. It's probably going to pick up a lot of images too. So let's take a look. All right, etc. So I was investigating the right area, just not quite close enough. Okay. So what I'm going to do with this, and copy that, and I will use our trusty text editor here to open this. And there will be a lot of options in here that I can't describe that are just for setting the configuration of FNIRT so that it performs optimally. So we can see some of the things are actually repeated on the command line just because we prefer explicitness over implicitness. So the reference specified in this configuration file is the same reference that we use in the command line. Same for the reference mask, same one. And then we get into a lot of these more particular parameters of the nonlinear registration algorithm. So again, here's another thing that we made explicit, the warp res, so approximate of the warp basis. So yeah, is essentially determining what is the best warp at a 10 by 10 by 10 resolution. If you wanted to be the most exact, you could find a warp at a 2 by 2 by 2 resolution. But that will probably take all day, and we don't have all day. So yeah, we have, and then we have a lot of these options here that I do not fully comprehend, but nonetheless, this is just to show you that this file exists, this config file. When we just specify it as the name, FSL knows just where to look. So they know that they keep all the configuration files in this directory. And when you specify a keyword that matches this name in this flag here, it'll automatically point you to this area over here. Okay. So another thing that we can do while this is running is that we can take a look at our FIN registration, see how good that was. So since this is actively running, I can't do it inside the Jupyter Notebook, but I can do it, if I can open this up, I can do it in our terminal. So again, CIU course, lab shady cat, 03 lab. Alright, then I'll do FSL view, sub 01, underscore T1. Actually, what we're supposed to name it again? Oh, dash T1. Yeah. Underscore F. And then sub. I guess a quick note about naming schemes. I will be talking about something called bids in the future. So how those usually work is that we have like key value pairs. So that in a very abstract sense put into practical means that sub is a key and then its value is 0, 1. And then ideally this would just be another label, or well, this is, did I say that backwards? Actually, this is a key, so sub is a key and 0, 1 is a value. All right. And then ideally this would be an underscore, so that separates the keys from each other so that we can tell that this is no longer part of the label, or part of the label or value. I use those interchangeably right there. But for this, we just named it like this, so we'll keep it like that. So we'll compare that to the MNI. Well, let's compare it to the brain, since that is what was exactly measured to compare with. So we'll open that up. We will see how good this looks. So right now the MNI is on top, so I put that on top. And we can look and see how different they are. You see it's alright. Typically, we can even see it here that the MNI brain is generally a little bit smaller than any subject brain that you're going to throw at it. But we can take a look just by changing the opacity of the top image to see how it compares to the bottom image. So affine, decent, but definitely could be improved upon. And since this is still running, I can show you guys one more thing, and then I'll just be talking randomly. So the one more thing that I can show is, oh no, okay, I finished. So I won't show you that one thing. So now we can take a look at those images that we just made with the nonlinear transform. So, yep. Right. Okay. And we can take another quick look here at the FNRT to see. Boom. See what some of the references are. So the IOUT is the name of the output image. So that's the one that we're most interested in. So yeah, the Jacobian field is kind of measure of fit. Yeah, I'm not going to describe those other ones. We don't need to understand those at a deep level. So FSL view, FSL view, sub dash 01. And this is going to be dash T1 underscore MNI. I guess it won't be. So yeah, so I guess since that one wasn't called with a, it uses the actual second iout command to specify the output of the image, so it essentially overwrote whatever this one specified. So we just have this image, so we'll FSL view that, and we will FSL view the MNI 2mm entirety. Okay. So again, do FSL view there. So you can see how good did this happen. So again, we can use the opacity to kind of switch around between the two. So yeah, in this instance, the shape has definitely been deformed even more to fit the MNI brain. And to make that even more realistic or more concrete, we'll also add the affine image so we can tell the difference between those two. Right? So I'll guess that one's on. Alright. So we can see that there's been a lot of deformations that occurred between the affine and the nonlinear transform until it's kind of changed the overall topology of the brain. Right, so you guys can see that. And now, the final step, we just did this to the whole head of the subject T1, and we want to apply that transformation to the brain. So we're going to copy paste the apply warp command, if we can find that baby. Alright, so take that, Control C, Control V. So again, we'll change this to our sub dash 01 underscore T1 weighted underscore brain. Just to make sure that that is the existing one. Yep. And then the reference is the 2mm brain. The output is, yeah, so T1. So I'll make this sub dash 01 dash just to remain consistent with that. And the warp, let's just look back up here to make sure what we called the warp, and then which one is the warp. So it is the cout is what we called the warp, and that is the file with the coefficients. So that'll tell us exactly how to apply the transformation to the file. Dash 01 C warp. Okay, so that's what we got for the warp. And now let's run this, because I think I changed everything that we need to do. I changed everything from the original command to our specific subject that we're doing for the homework. And we will run that. And now, finally, we will plot it. So again, waste not, want not. We will, I guess I don't know if we did this in class, so I will, let's see, do we even, yeah, let me run this again. So I'll do plotting dot. Actually, I think I'm going just to take a quick look at this, at the documentation here. So I'm going to do nylearn how to plot edges. So let's see if I can find an example that does what I want. So I'll click that. Okay. So I'll do not with that. Okay. So say, I don't think I need to do it with plot epi, do I? Just nylearn. Okay, so I'll just do it as they tell me to do it here. And I will do plotting dot plot nat. And I think that the image is going to be equal to our MNI brain that we used. Let's see what that looks like. So I guess maybe I need to look at the documentation some more. Actually read it, and add image. Okay. And add image. Okay. That looks like what I want. So I'll call that display equals that. And then I'll say display dot add edges. That is what we called there. Yeah, then we'll do add edges, and for that we will add this output that we just made. And we'll see, okay. And then I'll go to change this to display mode equals ortho. Or we can just do it as we did in the previous lab, where it's just the z cuts as we travel upwards. Then to learn that, let's take a look back at the plot and that. So display, we can just go with Z. And then this can be a tuple of floats or an integer. So then if I do cut chords 10, then it will just be the number of cuts. I can do cut chords equals 10. I think that is right. Okay. And now we can see how it overlays on the actual image. Alright, so as you can see, I'm still pretty nascent too when it comes to these plotting functions and have to look at the documentation, but hopefully that helps you guys with your own searching when you're thinking about, oh, how do I do this? Documentation is the very best place to check. Alright, I think I've covered everything. There was that one little surprise at the end, which I can tell you about briefly. Otherwise, you can just stop watching the video. It's been long enough already. So I'm going to go here, and this is something called FMRI Prep. So kind of what we've been teaching you is how to hand or like show your work and do things very manually. So an analogous way of thinking this is we're teaching you how to do all the calculations by hand, while in reality there may exist a calculator that does this all for you. So this is that calculator. It's still fairly new, so it doesn't fit all use cases, so it's not as ubiquitous as the calculator is, but this is called FMRI Prep, and it does once your data are organized in a very specified way, it will run everything for you, such as registration and extracting confounds and a lot of things that we haven't even covered yet. So we can even just look at here. Here's one of the older adult subjects. Now we can see with just some of these slices, we can tell that their brain, very large ventricles. So we can tell that this is a more aged brain just through that. And here is their estimation of the brain into M&I space. So we can see with their registration method, again, very good alignment. There's been a lot of changes to the actual anatomy of the person's brain, and we can see some types of squishing or some squeezing where things look a little bit weird, but that's usually just the case of going through the exact center of the brain, through the falx cerebri. There's usually some weird stuff that goes on there. But yeah, we can see that the normalization of the subject's tissue to the M&I brain is very, very close. So the changes that they made in order to align these images have worked very well. Right, and they do not use FSL, they use something called ANTS, and that's yeah, just a little bit more advanced than what we're going to cover in this class. So yes, FMRI Prep, it's the great equalizer of analysis packages. It allows anyone to complete these types of analyses. But yeah, I think it'll be very popular in the near future, and we'll see if we get time to show you guys more about this as well. Alright, but thank you all for listening. I'm going to finish this now before I talk for an entire hour.